Hi, I'm Annika, and for my physics project I decided to make a catapult. To make it a little bit more fun, I decided to make a cookie catapult, which you can launch cookies, donuts, and other fun things from. This is our basic diagram. We're going to make a basic framework out of wood. This is our arm where we'll be putting our cookie tray on, which will launch the cookies forward. The bungee will be acting as our spring so that when the release launches the arm forward, the bungee will be pulling it back. Now instead of just pulling back the release, we're going to hit the release at this target with a hard object or with a ball. Once the target is released and the release is released, the cookie tray will be launched forward, turning on the pivot point, being pulled back by the bungee. Okay, these are our basic materials and tools we're going to be using. We will use basic 2x4s to create the framework, screws and pivot screws to hold everything in place, a tray where the cookies and marshmallows will be launched from, these pieces of metal to act as the release, the springs, or also the bungees, which will be pulling the arm forward, launching the cookies. Now we have the cookies, the marshmallows, and the tennis balls, which will hit the target, releasing the arm. The tools we're going to use include a miter saw to cut the wood, a power drill, protective eyewear, earmuffs, gloves, a wrench, a pencil, a tape measure, and a clamp. Also, my brother will be helping me construct the catapult. At first, we are going to cut all of the wood pieces to build our basic frame. Okay, now that we are done cutting up our wood pieces, we're going to start to assemble our basic frame. Okay, we are now done building our basic frame. Now the really important part of the catapult, the arm, is going to be attached right here. We are going to drill a hole through and attach a pivot screw so that the arm can turn like this. Okay, so now that we have created our arm, we have also created our target post, which also has the release attached to it. So this is going to be our release. The target is going to be up here, so that when the target is knocked back, the release is pulled back and the arm will swing forward, launching the cookie forward. We are also going to put another pivot screw through the target post at the very bottom. Okay, we are now getting to the really important part of the catapult, the bungees. So we are going to attach one hook here and one hook down there, and then stretch the bungee like this, so that when the release is pushed back, that's what's going to give the arm its pull to launch forward. Okay, we have now attached the hooks. I'm going to demonstrate how the bungees work. Okay, so you're going to pull the arm through, hook it on the release, and now if you had a target here, you would throw the ball would hit the target, and the release would be loosened, and the arm would pull through. Now that our catapult is done, before I show you how to launch the desserts, I'm going to show you the physics going on. So basically, once I lock the arm into place and put the marshmallow on it, the bungees are being pulled back, storing a lot of potential energy within the bungees, so that when I hit the target with the tennis ball, all of the potential energy is being transformed into kinetic energy. Now, another thing going on here is the conservation of momentum. That is why we have this piece of wood right here. So that when the arm is released, the arm is stopped by the wood, but the marshmallow keeps on flying in the same vector direction because it still has all of that energy and momentum stored in it. Okay, and now eventually it will hit the ground due to gravity, because it will make that arc and then gravity will kick in and it will land. Okay, now for the fun part, the demonstration of the dessert launching. Okay, to quantify some of the physics we were talking about earlier, we want to see how far the objects fly. So, to make the aerodynamics a little bit better, we're using a heavier object, so a tennis ball, to see the distance of the flight. Okay, the starting height is 26 inches. Okay, and now we are going to weigh the tennis ball. 56 grams. 57 grams. Our final data point is going to be the amount of energy stored in the bungees. Okay, we are now also going to measure the energy stored in the bungees after the arm has been released. That difference makes up the amount of energy used. Later I will calculate if the data I recorded corresponds to the physics theory. Okay, we are now going to try and quantify the results we got from our catapult. So, to review, this is our basic frame, this is our arm locked into position, and this is our arm after it has been released. Now, the bungee, just laying on the ground, is 50 centimeters long. The bungee, completely stretched and locked into place, has a length of 104 centimeters. After it has been released, it is still stretched, but not as much, making it 83 centimeters long. The total Newton energy within the stretched bungee is 180 newtons, and in the released one, it is 100 newtons. Okay, we are now going to calculate the total potential energy of the bungees. So, the effective force of when the arm is locked into place is 180 newtons, and the effective distance is 0.54 meters. When the arm is released, the effective force is 100 newtons, and the effective distance is 0.33 meters. Now, after we have calculated, now that we know the forces of both released and not released arms is 180 minus 100, so the overall force is 80 newtons. Now, because the bungee is pulling at a diagonal, we can only use a portion of the overall energy, or overall force, so that we're going to multiply it by the sine of 30, which leaves us with 40 newtons. Now we are going to plug all of these numbers into the potential energy of a spring equation, which is 1/2 times F pull times the effective distance, which leaves us with 4.2 Newton meters as our potential energy in the bungees. Okay, we are now going to transform our potential energy into kinetic energy and to the ball's velocity at liftoff. So our potential energy is going to be transformed into kinetic energy, which the equation is 1/2 times mass times velocity squared. So earlier our potential energy was 4.2 Newton meters, which we are going to split in half between the ball and the stopper. So it's going to be 2.1 Newton meters. We are going to plug this into the equation of velocity and find out that the velocity of the ball is 8.5 meters per second. Okay, we are now going to calculate the horizontal and vertical velocity. We're going to be splitting the diagonal vector velocity right here into the vertical and horizontal velocity. We are going to be using the 40 degree angle of the release and plug them into the sine and cosine equations, giving us 5.46 meters per second and 6.5 meters per second as our answers. Okay, now we have all the information to calculate the flight arc of our ball. First, we will calculate how long it takes the ball to reach the top point. Second, we will calculate how long it takes the ball to go from the top point to the bottom. And third, we will calculate the distance the ball flies from beginning point all the way to the bottom. Okay, now the first section. The principle is that the moment from liftoff, our ball starts getting slowed down by gravity until its vertical velocity is finally 0. With all the numbers plugged in, we get 0.57 seconds. Now we'll use the acceleration for distance equation, plug in our 0.57 seconds, and this way we get the top height of the ball. Of course, we also need to add our starting height of 0.9 meters. Now our final top height is 2.42 meters. Now that the ball is at the top, we want to calculate how long it will take the ball to fall back down to the ground. We'll use the same acceleration for distance equation, and once we plug in our top height of 2.42 meters, we'll get 0.49 seconds for the ball to hit the ground. Okay, now we know the total time the ball is airborne is t rise plus t fall. So our total flight time is 1.05 seconds. By using the horizontal velocity component of our ball, we can calculate the distance the ball flies from its liftoff until it hits the ground. The equation we're using is distance equals velocity times time. Once we plug in the numbers, we get our total distance, which is 6.84 meters. Okay, if we compare our calculated distance of 6.8 meters to our measured distance of 18 feet or 5.5 meters, we were pretty accurate. The slight difference we attribute to slightly inaccurate measurements and the air resistance. Okay, that concludes my physics project. Have a nice summer!